Okay, good morning, everyone. We would like to welcome you to our very first Salon speaker series for the HBCU Data Science Consortium. We are very excited that you all took your time on a Friday to spend time with us and to hear a little bit about some very exciting things that are happening in the area of data science. We will be hearing from two esteemed professors at University of South Florida, which I will introduce shortly. So let's go ahead and move right on into some brief housekeeping announcements, and then we will move right on into our talk. Just to give you some overview of how the session will go today, we will, again, I will briefly introduce the speakers, and then I will stop sharing my screen and they will begin to share their screen, give you their presentation. Then we will set aside about a 15-minute question and answer session. So if you have questions, excuse me, if you have questions, please type them in the chat. You can also utilize the type them in the Q&A page button. You can hit the Q&A button on your Zoom to type your questions, but you can also utilize the chat to share ideas, or if you want to comment and say, wow, that was a very fantastic theory that one of the two speakers talks about, or you'd like to share a link that might be related to what they're talking about, feel free to utilize that too. And then we will close out the session by giving you the date and the speaker for our next session, which will be in April of this year, next month. So I will move on now and introduce our speakers today. So we will be hearing from Dr. Timothy Dixon and Dr. Yasin Yilmaz. Hopefully I'm not butchering your name. But they're both at the University of South Florida, Tampa, and they are speaking on our research pillar. If you were at the inaugural workshop, the way our consortium is set up is around 4 pillars, which are research, education, industry, and inclusion. And so they're presenting from the research side of data science to talk about some of the work that they're doing. You see the title there, which was also on your flyer that you received. And we will be hearing from them. They will talk about what they're doing. So Tim studies earthquakes and other natural hazards with microwave remote sensing and geodetic techniques such as GPS and ground-based and satellite radar. Yasin directs the Secure and Intelligent Systems Lab at USF. His research focuses on online machine learning, anomaly detection, and multimodal data fusion with applications in various domains, including environmental systems, transportation systems, communication systems, and computer vision. So I welcome our speakers today, and I will stop sharing now and turn the floor over to them.
All right, good morning, everyone. Today, Yasin and I are going to try to do something we have never done before, which is give a PowerPoint together, PowerPoint lecture. The topic is something we've worked on together for a while, but we've never actually talked about it. So the idea is that subduction zones are the focus of a very large killer, really, of people and cause of a lot of economic losses because of earthquakes and tsunamis. Scientists who study earthquakes and tsunamis have learned a lot about them from a combination of seismology, recording the earthquakes, and geodesy, which is the science of measuring how the Earth's surface moves. But we are inundated with data. We probably look at less than 5% of it. And about a year ago, Yasin and I teamed up to see if some of these new machine learning and artificial intelligence techniques could help Earth scientists do a better job of understanding these events, and then hopefully allowing us to improve forecasting. Okay, next slide. All right, so here's a quote from my favorite geologist from about a century ago, G.K. Gilbert. The people of the civilized Earth, the lay clients of the seismologist, would be glad to know whether the time has yet come for a scientific forecast of the impending tremor. So that was more than a century ago that Gilbert made that challenge to the scientific community. Next slide, please. And what's happened is that we've basically failed. You probably have read about or heard about the giant earthquakes and tsunamis that happened in Sumatra in 2004, which killed about 250,000 people. Most of those deaths were from the tsunami itself. And then in 2011, a magnitude 9 earthquake and tsunami hit Japan. That had the distinction of being the costliest natural disaster ever recorded in history, more than $200 billion and counting. Most of those damages were from the tsunami. And most of those damages were, in fact, from the tsunami destroying the nuclear power plant at Fukushima and then contaminating a vast area of northern Japan. And the cleanup from that event is still going on. So we have to do a better job. Next slide. Yeah, we need a better way to forecast. Okay, so you may have heard of the ring of fire. It's just a term that geologists use to describe where most of these events occur. They occur mostly around the rim of the Pacific, as well as into Indonesia over there on the left. And the reason is that these are places where the oceanic plates, the floor of the Pacific Ocean basically is subducted beneath the adjacent continent. Subduction just means it's being pushed under the edge of the continent. So I think the next slide is my movie. Let's see if that works. And the movie is going to attempt to show you what happens in a subduction zone that causes these earthquakes and tsunamis, and then how can we make measurements that might help us understand them. So the idea is that the lower plate, the subduction plate, which is the floor of the ocean, the Pacific, basically is being pushed underneath a continent, either North America in this example or South America in other examples. And as it pushes the leading edge of the continental plate, the continental plate gets compressed. And this goes on for a while until the continental plate says, well, I've had enough. And so it springs back. And the spring analogy is quite important here. So let's play that movie again and watch how the leading edge of the upper plate, North America, is pushed inland towards the east. And it does for a while, and then it springs back. And watch the ocean. You'll see how the tsunami happens. Right there. Yeah. So we can measure the motion of this upper plate with GPS. I've got 3 of them listed here, but we actually use dozens. Okay, we can go to the next slide. That spring analogy is quite important because the spring is storing up elastic strain, and then that strain is going to be released suddenly in the earthquake. So we have 2 phases. We got the spring moving to the right, which is to the east, and then it jumps back to the left, which is the west, if we're on the eastern side of the Pacific. So how do we do a better job of measuring this? Next slide, or next part. So there's 2 things that we can do. We can look at smaller earthquakes that happen before the big earthquake. We call those foreshocks. But we don't always get foreshocks, and we're not sure why. Sometimes we do, sometimes we don't. The other thing we can do is we can look at a type of small earthquake called slow earthquakes and slow slip events. And I'll talk about slow slip events in the next few slides. Both of these are recorded by seismic data and geodetic data. The seismic data comes from seismograms that record shaking of the earth. The geodetic data mostly comes from GPS. And so these 2 data sets together measure how the earth moves. So the 2 little diagrams on the lower right show what a seismogram looks like. And then the lower one beneath that shows some longer period perturbations in the earth that we can measure with GPS. Okay, next slide. All right, so this brings up 4 questions that are sort of related. The first one is, can we measure a strain budget? That is, how much does that spring compress? And can we use that information to forecast the location and the size of the earthquake? A related question is, is all the accumulated strain released in the next earthquake, or can some of that spring energy be stored over several seismic cycles, such that you might have three major earthquakes over several hundred years, and then at 1,000 years, you might have a massive one because the spring has been storing up some energy. The third question is, can we identify patches on the subduction plate interface, we call those asperities, that are high up on that subduction zone, underwater, under the ocean, under the coastal area? Can we identify these asperities that temporarily store strain and then release it and contribute extra energy to tsunamis? We actually think that that goes on some of the time. And then the fourth obvious question is, can we use machine learning to get a better handle on these estimates of strain and the preceding three questions? Okay, next slide. All right, I'm going to show you now some data from an experiment I've been running for about 20 years. It's in the northern part of Costa Rica called the Nakoya Peninsula. And there's several reasons why we went there. The first one is it has a big peninsula that provides us some land areas close to the trench, the thing that marks the subduction boundary. And we want to get our instruments as close as possible to where the action is. The other reason we went there is that this area had a history of pretty big earthquakes happening roughly every 50 years. They had one in 1853, it had one in 1900, and it had one in 1950. So around 2000, some of us got the idea, you know, maybe there's another one coming there. Why don't we put some instruments out there and maybe we can trap it and learn something? So that's what we did. Next slide, please. So around 2000, we started writing proposals. We got funded in 2003, and we got our first instruments in 2003. And the earthquake happened in 2012. So in some ways, we got lucky. The earthquake was a little bit late, which allowed us to get all of our equipment in. And the big earthquake was recorded by a few more than a dozen GPS stations and a very robust seismic network. And we're going to use these results, the data from these results, we're going to hindcast and look back at them and say, okay, what could we have done better to forecast this earthquake? Next slide. Okay, so this is the only equation I'm going to show. Yasin's got a few more, but this is my only one. And all it says is that the seismic moment, a moment is the word that seismologists use for energy. So basically the energy released in an earthquake is proportional to just two things: the area, A, that slipped in the earthquake, and the displacement, U, how much the earth moved on that area. And then the proportionality constant is this thing, mu, the Greek letter mu, and that's called the rigidity. But it really is just the slip area, how big of a patch slipped and how much it slipped, the displacement. So these parameters A and U are very closely related to the pre-earthquake strain accumulation. If the spring doesn't compress, you can't have the spring release. And so what we're trying to do with geodesy is basically measure these two quantities, A and U. So that's, we think, is the route to forecasting. Okay, next slide. So of course, life is a little more complicated. It's not just some nice big smooth patch A. It turns out that there's different patches and you have to kind of add up all the red zones to get the full A. You may hear me in this talk use the terms velocity strengthening and velocity weakening. And all that means is that once things start to slip in an earthquake, the friction is reduced and the earth speeds up. That's called velocity weakening. As the speed of the earth increases, its resistance reduces, and that's kind of the frictional criteria for having an earthquake. So the red areas are velocity weakening. The opposite is velocity strengthening. The earth starts to move and the frictional resistance to motion increases, and so the motion stops. And so in the old days, about 20 years ago, people used to think that you only had velocity weakening behavior in these red zones, kind of down dip from the trench up here. And this upper part was always velocity strengthening. And we now think that that's no longer true, that there's a time variability to this sort of behavior. Next slide. And in particular, we think that some of the time, this thing that most of the time is called stable or aseismic or velocity strengthening, we think that some of the time there's a switch flipped and it turns into an earthquake and tsunami generator. So it turns from velocity weakening to velocity strengthening. We don't know why that happens, but we think it happens once in a while, and that's when you get those really big tsunamis. So somehow we're going to have to figure out a way to put instruments out here and do a better job of understanding what's going on. Okay, next slide. So tsunamis imply shallow coseismic slip. We think that they do require strain accumulation. And we think that the mechanism by which that switch flips and changes that upper part of the plate interface from velocity weakening to velocity strengthening, part of the answer are these things called slow slip events, because they indicate special frictional conditions. And more importantly, they incur offshore the places where tsunamis start. Okay, next slide. So what are slow slip events? Well, they're actually similar to earthquakes, but instead of happening over a few seconds, they happen over a few weeks. We can measure them with geodesy, and we've been doing that for about 20 years. They are accompanied by this strange thing called seismic tremor and low frequency earthquakes, but we've only learned that in the last decade or two because we had to first detect these events. Why are they important? Well, the main reason they're important is that they wind up releasing a lot of the energy that normally accumulates in a subduction zone. They release an equivalent to a magnitude 7 earthquake every few years. So if we didn't have these slow slip events, we'd have a much bigger problem with earthquakes than we do today. So that's an interesting kind of sidebar on this story. Next slide. Okay, so what's a GPS network look like? Well, here's what a GPS station looks like. Here's one of my students putting it in. There's the GPS antenna. It's mounted on a rod that we pound into the ground to keep it kind of stable. We cover it with a plastic cover called a radome, which keeps the bird poop off it and a few other things. Here it is installed, and in the foreground, you can see a solar panel that keeps everything powered. Here's another view of the solar panel up here. And then there's this little steel box where the batteries go that the solar panels charge, and that keeps everything running. And then up here, you can just see a little flashy yellow. That's the GPS receiver. It's no bigger than a laptop computer. Next slide. So we've spent a couple of decades installing and refining this network. Here's a current map of the network. Every little dot there, red dot or red circle, is a GPS station. And then you see these funny beach balls, and they're the locations of big earthquakes that have happened in the last few decades. And the big one here is this magnitude 7.6 earthquake that happened in 2012. And we're going to talk about that a little bit more. The other thing this slide shows is a map of what geologists like to call the plate distribution. The surface of the earth is composed of about a dozen plates. Central America is the leading edge of something we call the Caribbean plate. Over here on the left is the Cocos plate, which is part of the Pacific seafloor. And basically the Cocos plate is moving to the northeast, kind of the direction of this yellow dotted line. And it dives underneath the leading edge of the Caribbean plate, starting at this feature here, which is a deep ocean trench. This is the deepest part of the ocean. I think in this part of the ocean, it's like maybe 6 kilometers deep. And then if you put contour lines, trying to make it like a topographic map on the top of the downgoing Cocos plate, here's those contour lines showing how deep it is. So back here, it's about 60 kilometers deep. Here, it's about 10 kilometers deep. Most of the earthquakes happen between about 15 kilometers depth and about, about 50 kilometers depth. So that's what we call the seismogenic zone. That's where all the action takes place in terms of earthquakes. There's one more number here. It's 77 millimeters per year, about 8 centimeters a year. What is that? That's about a length of that much. Every year, the Cocos Plate dives underneath the Caribbean Plate by that much. And so that's the thing, the process that causes all these earthquakes. Okay, next slide. So here's what some data looks like. Basically, remember from our cartoon, the GPS is being pushed inland. So it's moving to the northeast for several years. And there's these little dips here. And then here's our earthquake. The station jumps back towards what would that be, the southwest. And then there's some interesting behavior here. We call this post-seismic slip. And here, now it gets back to this normal behavior between the earthquakes. This will go on for the next 50 years. And you can see these little blips every 2 years or so. That's what a slow slip event looks like. So it's basically a little earthquake, right? So here was the strain accumulation phase. The spring is shortening. So that's what this part of the time series is doing. And then when the time series either goes down or goes in this direction here, that's a strain release. Here's an earthquake strain release, and here's a slow slip strain release. And they're easily identified, and they're not as big as earthquakes. And notice that the earthquake, of course, it happens instantaneously over a few minutes. So it's a vertical line on this time series plot. But the slow slip events have slopes because they transpire over several weeks to perhaps a month or two. Okay, next slide. Okay, so if you think about that spring analogy, there's an earthquake which jumps all the stations to the southwest and going down and to the left. There's slow slip events which are in the same direction but are smaller. And so all these colored arrows are the various slow slip events that affected these stations over about a decade. And then in between the slow slip events, they're moving in the opposite direction. That's what those gray arrows are. So the units here are interesting. So the slow slip events, we measure those in centimeters, how the Earth moved a centimeter or two. But in between, we measure that in velocity. How fast is that crust moving? And a typical velocity might be 1 or 2 centimeters a year. So this is the sort of data that we use to do our studies. And of course, it only works onshore, right? We can't make these measurements offshore because electromagnetic radiation doesn't pass through seawater. So even though we think this is where a lot of the action takes place, we're basically blind. So we spend a lot of time trying to figure out how to use the data from the inland stations to guesstimate what's happening offshore. And if I have a few minutes at the end, I'll address some new technology that might help us out here. Okay, next slide. Now it turns out we can take those displacement or velocity data and we can invert it and we can estimate what's actually happening down at the interface beneath our feet, the interface between the Cocos and the Caribbean plates, because that's where the earthquake is going to generate. And when we do that, we find that there's 2 locked patches. Remember my cartoon of the Asperities that tried to figure out, which are the lock patches? Well, here they are. So there's one lock patch here, and there's one lock patch here. And so this is pretty interesting because in the next few slides, you're going to find out that it's this lock patch that ruptured in the earthquake of 2012. But this lock patch didn't. And the reason it didn't is because this is where all these slow slip events happen, releasing the strain. Okay, next slide. Okay, so if we take our 2-decade-long time series and add it up and say, where did all the slow slip happen? What we find is that there's a patch of offshore slow slip here, and there's a patch of onshore down dip slow slip here. And this one was the strongest. And in fact, it matches all of the strain accumulation that we estimate from GPS. In other words, all of the energy in that spring got released here by slow slip events. If you can see, kind of do the math here. I think these contours are they're in millimeters. So there's like 2 meters of slip that got released here. And here is where the earthquake happened in 2012. And there's contours again in millimeters, but in blue that show how much the earth ruptured. Remember my equation, M and A? Well, here's the A, this blue, the outer blue contour shows where the slip more or less ended. And then the numbers here are the U, the displacement. These are the amount the earth ruptured in millimeters. And so we now see that the earthquake happened where the slow slip did not. The slow slip happened all around, but it didn't happen in here in the middle, and that's where we had the earthquake. Okay, next slide. We've done a check on this. Here's some more recent data after the earthquake. Actually, this one on the left is before the earthquake. This one on the right is after. And so this patch of deep slow slip, this is around about 40 kilometers depth. That's a persistent feature of this subduction zone. We don't know why it's there. It might have to do with a subducted seamount. A seamount is just an underwater volcano, but we're not sure about that. But the point is that all of the strain that accumulated in a 5-year period or so is released by this slow slip. Here's the units of the amount of slip in these slow slip events. And here's those blue contours again from a different author, and they sort of match what the other author showed. So we have a nice picture here that there's slow slip happens in one place, the earthquake happens in another. And so if we can measure reliably these slow slip events and where they occur, where the A is and how much the U is, we have a way of telling how much of an area could slip in the next earthquake. So that would be an improvement in our ability to forecast. Now, offshore is a different story. The offshore slow slip is not enough to release all the strain. So it is possible in the future there could be a tsunami generated here. The 2012 earthquake did not generate a tsunami for reasons that we don't fully understand, I should say. Okay, next slide. Okay, I think I've said most of this, except for the last thing. So I've said that a lot of action happens offshore. We need to understand if the offshore slow slips are releasing strain or accumulating strain. And to do that, we need to figure out a way to get our instruments out onto the seafloor. Next slide. So one way of doing that is to recognize that a lot of this offshore stuff, while it's underwater, it's not very deep. So here on the left, I'll just talk about this one on the left. Here's our Nakoya Peninsula that we've been talking about. Notice just to the north west, there's a big patch of red. That red is water where water depths are less than about 150, 200 meters. So that's not that deep. There's a lot of shallow real estate out there. Next slide. So we've proposed to take advantage of this shallow water and basically build a GPS station there. And the way it would work is you'd get this big cement block down there. You'd anchor it with a chain or something else. You put a float to keep the thing vertical. The water line would be about here. And then you have this pole sticking up. And on the top of it, you put a GPS receiver. So it would be almost like having a GPS receiver on land, except you've got this long pole and you need to correct for its motion from winds and currents. And of course, you'd have to make the whole thing strong enough to withstand, cyclones and hurricanes and all that stuff. So it sounds like a kind of a crazy idea, but we've done it. Next slide, please. So a few years ago, we built this thing and we put it out. We were testing it in Tampa Bay, and here's a picture of it. The upper portion, the underwater portion, obviously you can't see, but here's the pole that sticks up. It's got some solar panels to keep it powered. It's got a radar reflector here so that ships don't run into it. And the batteries and the GPS receiver are there. Here's another radar reflector. And then right at the very top, you can just make out the GPS antenna. So this thing has been working now for a couple of years. It's in a test mode. And we hope to modify this design and make it work in even deep in water and then put it offshore Central America. Next slide. Okay, so yeah, here's the future work. We'd like to build a deeper water version. We'd like to deploy it to Central America and to other subduction zones. And then, of course, we'd like to apply machine learning to data from that buoy and to all of our onshore data to get a better handle on some of these events. The data sets are rich. We're missing a lot of stuff. And this is where Yasin's colleagues and Yasin's work comes in, because we need his expertise and machine learning techniques to do a better job of analyzing these time series. So now I'm going to turn it over to Yasin, and he'll tell you how he's going to work his miracles with artificial intelligence.
Thank you, Tim. Thanks also for your nice words. I'm a data scientist. I'm a professor in electrical engineering department, and I've been working on signal processing and data science since my master's, actually. So I'm just gonna talk about one possible idea, to improve the earthquake forecasting techniques that Tim and the other geoscientists have been working on. So this is just maybe a drop in the ocean. I mean, that could be done using machine learning. And this is just the beginning of this, actually, let me say, adventure, because not a lot of work has been done in this area using machine learning and data science for geoscience. So especially in this subduction zone problem, that's what we see. In the literature, there is relatively more work regarding more general earthquake studies, studying big earthquakes, but understanding those precursors, slow earthquakes, slow slip events, is an uncharted territory right now for data science. So we have some ideas. These are just some, still preliminary ideas, and we hope to work on these ideas and get some real results soon. I will now give you some overview of what I've been thinking about, how to improve these studies. So I will talk about multimodal data fusion, and the technique that we plan to use for this data fusion task is representation learning. It is based on deep neural networks, and to learn some representations, as the name says, representations of complex data, complex time series data. Can we learn some good summaries, good representations which could be useful for making inference about the physics behind this problem? So this is an overview of my slides. I will first describe what multimodal data fusion is. And then specifically for this earthquake forecasting problem, I will talk about two models that we plan to work on. One is a classification model, a supervised learning problem for detecting small earthquakes. And the other one is about an unsupervised learning problem. So we will use similar neural network deep learning techniques, but this time not for classifying an earthquake, but for more theoretical question, to understand, to help geoscientists understand this physical process. Can we provide some good summaries for building intuition? So that's the third bullet point, are generative models for process understanding. And finally, I will show some real data results that we had on other data science applications. As I said, unfortunately, in this problem, we don't have results yet on this earthquake detection or understanding problem, but I have results on some other data science applications using the techniques that I'm going to mention. Okay, so what is multimodal data fusion? In many problems, engineering problems or scientific problems, we have data coming from heterogeneous data coming from different resources. In this specific problem, as Tim said, we have seismic data shown here, which is very high frequency data, and it's about the vibration of the Earth. And these data points are every milliseconds. Okay, so this is very high frequency data. The sampling frequency is very high. And about the same problem, we have also geodetic data, which is quite different. It's, we are observing the same system. We are looking to the Earth, the movements of the Earth. In the first one, we are looking at the vibrations of the Earth crust. And in this geodetic data, we are looking into the movements of the Earth, but the sampling frequency is quite different. As Tim just described, now we are talking about weeks instead of milliseconds. So that's a huge difference, right? These data types are quite distinct. And yet we want to use them together because they are coming from the same physical phenomena, right? The Earth crust moves. One is a very slow move, the other one is a fast move, but we don't have all the time both of them together. Sometimes we have them measured both of them together, sometimes not. So we want to use these two data sources together jointly. That's the data fusion problem. And actually you can say, okay, these have been already in use, right? There are geodesists using geodetic data, there are seismologists using seismic data, but the problem for us here is to jointly use them. The common practice in this domain and also in many other data science domain which involve such disparate data types is to separately analyze different data modalities because it's easier. That's the easy way to do. So practical simplicity is an advantage actually. We like simple things. I mean, that's a positive thing. But there's a big disadvantage in terms of the performance and the information that we can leverage to solve the problem. So what I mean by using these data types separately is that you use, for example, the seismic data to detect a slow earthquake, and then you use this geodetic data using geodesy techniques, okay, separately to again detect a slow earthquake, and then you try to combine the outputs, the results of these two parallel data processing streams. This is called decision fusion because we are processing them separately, and then we are trying to fuse only the decisions. Okay. But here again, the problem that we don't like, the disadvantage is that we are losing the cross information between the data modalities. A better approach that would not lose that information is jointly analyzing these different data sources. That's our goal here. Okay, by data fusion, I mean jointly analyzing the different data modalities. Instead of decision fusion, we want to fuse the data at the raw data as much as possible. Okay, so hopefully this will help us to have a better detection and understanding of typical earthquakes because we won't be losing the cross information between them. Okay, so what does that mean? Again, let me give you an example. If you first, for example, use seismic data to see if there's a slow earthquake, you may see that, yes, we detect a slow earthquake in this bunch of data, and then use the geodetic data. And if you are lucky, if you again, detect, and assume that they're synchronized from the same location, from the same time period, and you again detect something, then you can fuse the decision, and then you can say, okay, with a high confidence, I can say that there was a slow earthquake in this location, within this period, because both my seismic data and geodetic data say so, right? And in another case, if you see that neither your seismic data nor geodetic data, tell you that there was a slow earthquake, then you can say again that, okay, none of them gave me a positive result, so I'm just inferring that there was no slow earthquake. So this is decision theory. But how about if one says yes, the other say no? Then there's an ambiguous case here, right? So and how about using those data types jointly to improve the performance? Because, for example, if there, we are talking about slow signal, very low amplitude signals here, okay, so slow earthquakes, which are difficult to detect actually. So if you have a detection in both signals, okay, this also does not necessarily mean that actually you have a very, you're almost sure that there was an earthquake, because in both of them you may have some error due to noise, okay, and these just may be coinciding, okay, those noise and error due to noise maybe just coinciding. So if you use joint analysis, you may discover that, okay, certain patterns appearing together actually are a real good signal for an earthquake. Then this contextual information, okay, a pattern in geodetic data appearing a certain pattern in seismic data is a really good signal, a signature, okay? That you cannot do with separate analysis, but with joint analysis you can do. So that's our goal, but we will of course pay a price here. There will be more challenges, more theoretical and practical challenges to do such joint analysis. Okay, so here's our first model. This is a classification model. It's called discriminative model, which means we have some database, seismic and geodetic database, and then we have the labels, ground truth labels, which means we know that in this period of time, in this location, there was an earthquake, in particular a small earthquake. And how do we know that? There's fortunately there's a huge earthquake catalog. As Tim said, they have been collecting data, seismic and geodetic data for a long time, and there's a very well documented earthquakes in this catalog. So we have labels, okay, we have historical data, we have labels. So our goal here is to build a machine learning model that can find a mapping, a computational mathematical mapping between the raw data and the label. This is a supervised classification problem. And what is the challenge here? Challenge is to use jointly the seismic data and geodetic data together, because supervised learning has been around for a long time. It's a well-studied problem. So, and this is a binary classification problem, looks like a simple problem, but the problem is here to jointly analyze the different data types. Here is a diagram that shows our idea. So we have the geodetic data, let's say, let's denote it with X, and then we have seismic data denoted by Y. We firstly synchronize them and obtain an heterogeneous data Z. We process, so our goal is to obtain a homogeneous summary of this heterogeneous data Z. And in between, we will use neural networks, in particular, recurrent neural networks, GX and GY, and we hope to find a probabilistic representation of this heterogeneous multimodal data Z. So the first step for us is to deal with the synchronization problems, and the biggest problem here is the very different sampling frequencies. The seismic data in the bottom has a very high sampling frequency at data point every millisecond, and the geodetic data has a low sampling frequency. We have a data point every minute or hour, maybe, okay? And the event time scale is also quite different. In seismic data, the events take place in seconds, but in geodetic data, events take place in weeks. So we this will be a big practical challenge, and we plan to synchronize them using the slower clock, which is the geodetic data here. Assume that, for example, we for an hour we collect seismic data and geodetic data. So of course there will be more seismic data than geodetic data, and then we form into data units called Z. And then we want to learn a representation of this heterogeneous data, which includes both seismic and geodetic data. And let's denote it with U. So U is a latent variable here. It is a summary in basic English terms. It's a summary of the heterogeneous data Z. So it's a vector. Okay, so Z is a time series. It's a complex data, and it's a two-dimensional, two-modality time series here. And U is just a vector. It's a homogeneous representation of the heterogeneous data. So that's the real challenge here, okay, in our problem. How to learn in an effective way this U representation. So some of the theoretical challenges are, overfitting. Let me briefly explain what overfitting is. If you build a very complex model, and nowadays we can do that using the advancements in deep learning techniques. You can build very deep neural networks which can discover very nonlinear relationships between the input data and the output label. But then there is usually the overfitting problem. We don't, because you can only build this model using a training data, and overfitting means that you are summarizing your training data and you're losing the generalization capability, because later on you will use this machine learning model for some new data, test data. Okay, if you summarize your training data, if you overfit all the ups and downs, all the noise processes in your training data, then you will have a very poor performance on your real unseen test data. So we have to deal with this problem. So to deal with this problem, we follow a Bayesian approach, and we want to learn actually not a deterministic description representation UI, but we want to learn a probabilistic representation of UI. And let's say we want to, since it's very tractable, we choose the Gaussian model shown here with script n. The Gaussian model has two parameters, mean and covariance matrix. So we want to learn the posterior mean and the covariance of UI, the latent representation. And the technique that we follow here is called variational autoencoding. We will use neural networks to map Zi, the heterogeneous time series data, to mu I and sigma I. Here's again our diagram. Now, I hope it is more clear. These neural networks GX and GY process the geodetic data and the seismic data to map them to the mean mu and the covariance matrix sigma. Okay, once we learn mu and sigma, which gives us that U representation, then we can use it for in a standard way for supervised learning, for classifying the small earthquakes. And how about the unsupervised learning problem for process understanding? Once we have the U representation, this latent representation UI, instead of using in a supervised learning manner, we can track its change. Okay, so this doesn't require any labels. Okay, we just have the seismic and geodetic data, and no need for the earthquake label. Now we just want to see how over time this summary representation changes. And to do that, we will use some advanced visualization techniques. And here we see an example that one of our collaborators has been developing. And this is called a manifold visualization technique. UI is like a summary manifold here. And as shown in this figure, if we can follow how it changes over time, then it can give some valuable insights to scientists. And this example is from actually sleep research. We see that our collaborator has provided us. It starts, at some point here, and then, so these different colors in the legend shown here in the legend are different phases of sleep. So over time, the brain signals, move, from one area in this two-dimensional graph to another area. So this kind of, change over time can give good insights to scientists. Okay, finally, I want to show you some results from our previous projects. So I know that I'm running out of time, so I will try to keep this short and quick. We worked on a Twitter dataset, a huge Twitter dataset in 2016, and we used the data from a dataset from 2014. This was a multimodal dataset, which includes the tweets, which are actually text, as you know, right? So text is one data form here, and the other data modality is the locations, the geolocations of these tweets. In many of the tweets, this is enabled by default. That was the case at least in 2014, and we have also counts of hashtags. Okay, so we organized this data set in terms of hashtags, and then we tried to detect real world events by organizing the hashtags. We tried to, and it's not an easy job because for a real world event, usually there are many hashtags. As you see here in 2014, there was a big real world event, some trend called Ice Bucket Challenge. So when we processed this data, we discovered latent representations, and this Ice Bucket Challenge was a global event back then, and its mean point, its geolocation, mean geolocation is in the middle of Atlantic Ocean, because there were many tweets coming from Europe, Asia, and then all over the world, and also from North America, South America. So its mean location point for this representation factor is in the middle of the Atlantic Ocean. And then this is the dominant hashtag about this summary vector, and then some of the dominant words, popular words, and some others, like there was back then, in that time, there was Commonwealth Games in Glasgow. As you see, the hashtags are relevant, the words are relevant, and then an event, a scandal about an Indian religious leader, in some hashtags words, and that was not just English, by the way, including many. So the original data set included many languages, but we actually focused on English, and the passing of Robin Williams and so on. And we also clustered the hashtags using those latent representations, summary representations, and we see a nice clustering results here. Robin Williams hashtags are clustered here. Local Ice Bucket Challenge and Global Ice Bucket Challenge, they're all clustered. And my last example is from a movie recommender system. We used a big data set called Movie Lens 1 million data set. And it is again multimodal. It has ratings, which are some integer values usually from 1 to 5. And there's age, again, an integer value. And then occupation is a categorical variable, which is not ordered. Which doesn't have any bigger or smaller relationship. It's purely categorical. And gender, male, female, and genre of the movies. And we show that when we use all this data jointly, not separately, because the standard techniques use them separately, and they mostly use only the ratings. We use that when you use site information provided by multimodal data, you can do a better job in recommender system. So we see on the left, we see some user profiles that were clustered together in the latent representation. And as you see, it's for humans, it makes sense, it's interpretable. The gender, the age, the occupation are all relevant. And also, more importantly, the movies they highly rated, their favorite movies, are all relevant from similar years, from similar genres, and some of them are the same movies even. And on the right, we show our the quality of our recommender system. So there were no many techniques which could be run on such a big data set. So we only compared with one technique here. Warm start refers to the easier case where you have ratings for the users that you want to test. And the cold start is the more difficult task where you don't have any ratings for a user. The user has just registered to the system, or maybe not, not a very active user. So it's a more difficult task to provide recommendations for such a user. And in both cases, we achieved a higher recall score, which measures the quality of recommendations, because we were able to utilize these multimodal site information, which the other methods can do not use, because it's a challenging task. Okay, so that's the end of my slides. I think it's time for questions. And sorry if I was too fast, so I just tried to stay within time limits. So yeah, Jason, you can, I think, take the mic.
Yes, so thank you all. Thank you both, Tim and Yasin, for your presentation. Very informative information. So attendees, if you have any questions, you can type them in the Q&A box. We've got time for a few questions here. I do have a couple of questions I wanted to kind of ask both of you. So we heard a lot about the work that you're doing. Very interesting work, and there may be individuals here from HBCUs that are interested in collaborating with you. So what suggestions or recommendations do you have for other schools that might be willing to or interested in trying to do some research work with you?
Yeah, Tim, do you want to go first?
Sure, I can take a stab at that. So I collaborate with a lot of people. I do it in two ways. For students that are interested in working with me, I encourage them to apply to graduate school and work on a PhD with me, because I depend on my graduate students to do a lot of the clever analysis. A lot of the work that I presented today was actually done by my graduate students over the last decade or so. But the second way I collaborate is I write proposals with people, and I write proposals with people all over the world, many of whom I've never met, because we have this thing now called email and the internet. So it's very, very easy to share ideas, bounce ideas back and forth via email or by Zoom meetings like this. And I often write proposals with people to NSF and NASA and other agencies to get research funds to explore some new idea, work in a different place. So those are two simple ways that I collaborate with folks at the grad student level and at the colleague and proposal level.
The same for me, and I just want to add one more thing, that we submitted a big proposal with Tim, and if this is successful, then we'll be looking for students. And diversity and inclusion is one of the, as yours, is also one of our pillars. So we'll be looking for new students, and there will be a lot of opportunities for students to be involved in our project.
So sort of as a piggyback to that question, then, if students were to apply for one of those opportunities, are you expecting them to have a significant math or computer science background, or what backgrounds in particular are you looking for from the student population?
So I get students from very diverse backgrounds. I'm a geologist. I think in my career, I've maybe had one geology student as a grad student. I've had people with electrical engineering background, people with physics backgrounds, people with computer science backgrounds. So I take students with a wide diversity of backgrounds. It is useful to have some math and engineering background, but the geology student I had did very well. They picked up a lot of the computer science and programming stuff. So I have students with very diverse backgrounds.
For me, it is usually background in electrical engineering and computer science, and in particular, we are looking for a good background in fundamental math and probability topics, and also coding, data science, coding. It's now dominantly Python, but not necessarily any good experience in other languages, including MATLAB. Is a very good advantage. So yeah, we when we receive CVs, we look into, in addition to GPAs, we look into those experiences in whether the student has done any research. So it depends on the experience level of the student. If it's an undergraduate student, GPA is more important. If it's a master's student, we also look for some evidence for for research. And yeah, basically it's mostly, for me, probability and math, linear algebra plus coding.
Gotcha. So one follow-up question to that. In those proposals that you submitted, are you going to be expecting or planning to have REUs or graduate level REUs with that students could apply for?
I don't think we put an undergrad REUs in that, did we, Yasin? It was mostly for grad students and postdocs.
Okay.
Yeah, but there is always opportunity for REUs. You can submit an REU supplement, and there are also local university sources. So yeah, that's a possibility. I mean, mostly the research will be will depend on the graduate students, but yeah, I'm sure there will be opportunities for REUs as well.
Gotcha. So one more question I have is related to the consortium. So we would definitely love to work with you on trying to do what we can to advertise and further your work. Do you have any suggestions for what we can do as a consortium to help further your efforts along?
Boy, we'll if it gets funded, we'll really need students. So advertising opportunities for grad student applications, that would be a great thing. I think it's starting in our second year, we're also going to have postdocs. So if you have more senior students that want to pursue postdoc opportunities, that's definitely a possibility.
Okay. All right. Do we have any other questions from the audience? Go ahead, Yasin. I'm sorry.
No, nothing to add. I just concur with him. And the postdoc opportunity will be an interesting one. It will be a cross-disciplinary, program. I mean, if the student, the PhD graduate, is from electrical engineering, computer science, he will work with a geoscientist. And if this PhD is from geoscience, he will work with a data scientist. So it will be a really good opportunity for interdisciplinary research.
All right. Well, once again, we thank you for your presentation. Definitely looking forward to working with you from a consortium standpoint, but also from our individual schools. We will definitely, look to try to get you some students that can work with you. You're right down the road from us, so it's a lot easier for us probably. But we will definitely be in touch with you. Keep us posted on the progress of what you're doing and the progress of your initiatives that you submitted proposals for. And we'll be looking forward to working with you going forward. So thank you again.
Great.
Very good. We look forward to working with you.
All right. So just to give you some announcements for next week or next month, our speaker next month will be Dr. Richard Allo, who's the Dean of the School of Science and Technology here at Florida A&M University. He spoke during our inaugural workshop as one of the educational panels. So he'll be talking a little bit about his research, but also talking about educational concepts. So I know at the workshop, there were people that were interested in degree curriculum development, program creation. And I know Dr. Allo, who's actually on this talk as an attendee, I know he is currently working to develop a bachelor's degree and I think a master's degree in data science. here at FAMU. So he would definitely be a resource for those of you that are interested in your own institutions and trying to build these programs out. So save that date. It's April 16th, same time, 11 a.m., 12. And we will send out an announcement to all of you that attended today, as well as we'll post it on our website, the link for you all to register when that's available. So we look forward to that. Okay, so thank you all for attending today. We definitely appreciate it, and we hope you got a lot out of it, and we will see you all in April. All right, thanks, Tim. Thanks, Yasin. Okay, I have 11 o'clock, so we will go ahead and proceed. Okay, I see a few members of our team here. I'm gonna promote them just so they can say hello. Good morning, Al. Good morning, Felicia.
Good morning.
Good morning.
It was bad. So.
Right. And I've lived down here a long time. I'm originally from New York, but I've lived down here a while and still have not gotten used to the pollen. It still affects me every year.
There's a lot of it. I mean, the oak trees are famous for putting out just a lot of pollen. I don't think anybody ever gets used to it.
Morning, work. Yeah. I'll call him back. And I was coming up with Ted and Karen. I talked to Karen in the later call. I closed. Well, you know what?
5 minutes, and then we'll have a Q&A after that.
Sounds good. How's the weather up there?
It is nice and hot again. We had some really bad rain yesterday, then that moved through. It's a little cloudy today, but it's nice, beautiful weather now. So how about down there?
Well, it's pretty much the same. We needed that rain. We had a lot of oak pollen floating around, and the rain kind of washed most of it down. So that was good.
we did too. And this time of year does the terrible things to my sinuses.
I love the oak trees, but especially this year, the pollen really got to me for just about
me too.
3 days.
All right. Well, I hit the button too. So now we're seeing attendees starting to roll in. So okay. All right.
So Jason, I think the way this will work, I'll probably talk most of the first half, and then Yasin will come in and talk most of the last half.
Okay. Sounds good. So yeah, I have a couple of slides at the beginning, and then I'll turn it over to you, and you all can proceed as you see fit for 30, 45 minutes. 40 to 40.